Hello, this video is on the derivation of the Michaelis Menten equation. It took me a while to figure out, so I thought I'd explain it so other people don't have to spend as long a time figuring it out as I did. So, in this video I'd like to explain how we get to it, what each term has within it, what other terms make up each term, if that makes sense. And in a subsequent video I'd like to explain what each term means in a clinical environment, what each term implies, and how to use it in your train of thought. So to start off with, here's the Michaelis Menten equation. The velocity starting out of an equation, of a reaction, is equal to the maximum velocity that's possible to obtain times the substrate concentration over Km, the Michaelis Menten constant, plus substrate concentration. To start with, let's do a quick review of reaction rate. If I have this reaction, A plus B goes to form P, and I want to find how fast P is being formed, then I'm going to be looking for the reaction rate equation. And another way to say how the velocity of P formation is dP over dt. So velocity equals dP over dt. If you haven't had calculus yet, think of this d right here as a delta. The change in the concentration of P over the change in time is equal to a rate constant, K, times the concentration of A, times the concentration of B. Now, this crazy looking thing down here is trying to show that this rate constant, K, has within it this term right here, delta G double cross. And this term signifies the amount of activation energy that's needed for this reaction to start. So, within the K term is the activation energy. Alright, continuing on. This is an enzyme substrate reaction. We have on this side starting enzyme plus the substrate goes to form an enzyme substrate complex. From here it has two choices. The one it most commonly takes goes back and regresses back into enzyme and substrate. But on rare occasion this ES can go forwards and form the product and then reform the enzyme. Each one of these steps has a rate constant going from E plus S to ES has K1, from ES to E plus S has K minus 1, and from ES to P plus E has K2. These numbers are arbitrary, they're just mainly to differentiate between which rate constant. So for the velocity of this reaction, we're trying to find out how fast this product is being formed, because this is what we care about, is the end product. So we're trying to find dP over dt. So let's look at this reaction. From the precursor, ES, we know we have this reaction constant. So K2 times the concentration of ES will give us the rate of P formation. Now, Michaelis Menten wanted to add some more details into this so that it could be looked at more objectively and have more factors to look at. So they thought, well, what changes this concentration? What changes the concentration of ES? Because whatever changes the concentration of ES is going to lead to a change in the concentration of P because of this formula right here. Now remember this formula right now for later. V equals K2 times ES. Alright, so we're looking at ES. And we want to find the change in ES over change in time, because if we find out the change in ES over change in time, we can find out the change in product over change in time. So when we look at that, we're going to look at all the reactions that bring things to or away from the ES. So right here, let's start with this. E plus S goes to form ES. So that's creating ES. So that's going to be a positive sign, and it has reaction rate constant K1. So it's K1 times the precursors, E and S concentration. Now going away from ES, we have this reaction and we have this reaction. So if we subtract, going this way first, if we subtract K minus 1, and we have ES as a precursor now because it's going this direction, ES is the precursor, so minus K to the negative 1 times ES, and then if we have on this side, going this direction, we have this rate constant times the concentration of ES, because it's a precursor, minus K2 times ES. That should give us the change in ES concentration over the change in time. Alright, so we are going to assume that K minus 1 is much, much greater than K2 for this equation. And this works in a lot of different enzyme reactions. It's very classic of enzyme reactions. So when we start out, we have E plus S going to ES, and really a lot of the time it's going to go just straight back. So that's what that's saying. K1 is much greater than K2. This happens a whole lot more than this happens. So if we do that, then the change in the concentration of ES over the change in time is going to be approximately 0. Now this is an assumption. In real life it's not 0, but this is an assumption that we do in order to calculate it easily. And we say it's almost 0 because if things are going E plus S and then going to ES and then going back and then going back and then going back and then going back, ES concentration isn't really changing. So that's what this is saying. The concentration in ES is not going to change over time. Now if we look at a graph of an actual real life sort of example, I got this from the source down here, and they had this orange box on here that I didn't take the time to take off, so this isn't important for me. But if we look at this right here, this level, or this side, y-axis represents the concentration, and the x-axis represents time. If we start at time of 0, we look at this enzyme right here, and it's at its highest level. That's because none of the enzyme has met with any of this substrate, which is also at its highest level because none of it has been broken down. The ES, the enzyme substrate complex, hasn't been formed yet, and product hasn't been formed yet, so they're both at 0. And now as we go along in time, this enzyme level is going to slowly fall because it's meeting with its substrate and forming this enzyme substrate complex. Also at the same time, the substrate's going to fall because it's being involved in the enzyme substrate complex, and the product is going to rise because very slowly the ES complex is going to go and make enzyme and product. So this is going up slowly. Now the part that we look at when we're doing Michaelis Menten equation is this region right here. This region right here on the x-axis. And the reason we look at that is because look at the concentration of ES. It's pretty constant. The change over time in ES is very minimal. So we approximate it to 0. Okay, so let's set dES over dt to 0. If we do that, we get 0 equals this mess up here. And now let's rearrange it real quick and get this. And now remember how we're trying to find out about the concentration of ES over the change in concentration of ES over time, because that will tell us the change in concentration of P over time. So let's solve this for the concentration of ES. And here it is solved for the concentration of ES. Now these three numbers right here are kind of cumbersome. So what Michaelis and Menten did is they came up with a constant that could replace these three. So it's the Michaelis Menten constant, and it's defined as Km equals k to the minus 1 plus k2 over k1. Now if you look at this equation, it's inversed. So when we put Km substituted in for this, it's going to be on bottom, and it's going to look like this. Concentration of ES equals concentration of E times concentration of S over Km. Now the next thing we want to do is we want to get rid of this term E, so we can put in some other terms that are more useful to us. The way we're going to do that is we're going to make a new equation. So here's our new equation. The enzyme total equals the amount of free enzyme plus the enzyme substrate complex concentration, which makes sense because if we put in 10 moles of an enzyme and one of it is free, not attached to a substrate, and 9 of the moles are attached to substrate, if we add the 9 moles of enzyme substrate complex plus the 1 mole of free, we get our original 10. So if we rearrange this to solve for E, so we can plug it into this E right here, we get E equals ET minus ES. And now let's put that into that equation on top, replacing this E, and we get ET, not the alien, it's the enzyme total, minus ES times S over the Michaelis Menten constant. Now we substituted something in, but we now do not have ES solved for. ES is in both sides of the equation. So let's do some fancy math, and we'll get ES equals ET times S over Km plus S. Now let's go back to the beginning. Remember that formula I told you to remember? This is where it comes into play. This is just a repetition of the previous slide, and right here we have Remember that the velocity of the formation of the product equals K2 times ES, because ES is the precursor, K2 is the rate constant, and that's how fast it's forming P. Well, we have ES right here solved for. Let's put this ES into here. Let's put this value into here and see what we get. This is what we get. The velocity at a certain point in time of the formation of the product is equal to K2 times ET times S over Km plus S. Now we have just one more step till we get to the Michaelis Menten equation, and that is to find the maximum velocity that's possible to obtain. And the way we're going to do that is by thinking, well, what makes a reaction go faster? Adding more substrate. If we max out the amount of substrate, have a substrate level of infinity, that's the fastest possible that reactions can go. So if you've had calculus, this is an easier concept to understand, but let's think of these two S's right here, substrate levels, as infinity. And I'll illustrate that right there. Now, we have something on top times infinity, and something on bottom plus infinity. Now think if you were, let's say this was 100 million. Think if you were a 100 millionaire, that'd be pretty nice. And let's say this value right here is 2. If you multiplied your $100 million by 2, do you think you would notice that? Probably, because that's a lot of money that you just gained. But down here, let's say this Km is 2. If I add 2 to $100 million, do you think you're really going to notice it? Now if this was higher numbers, let's say a billion, it's going to be 2 billion versus a billion and 2. As you can see, as this number gets higher, this number becomes less and less important, and this number stays just as important. So we're going to, since this is so high, we're going to get rid of Km because it's no longer important. Alright, now I have this. I have a huge number over a huge number, but remember it's S over S, so anything over itself is divisible by itself and it equals 1. So I'm going to cross those off and put a 1, and I get the maximum velocity that's possible to obtain is K2 times ET. Now wait, if I look up here, I notice K2 times ET is already in this equation. What if I substituted K2 plus ET for Vmax in this equation? So what if I took out this and instead replaced it with Vmax? And that's how the formula is calculated. Now there's one more important element that we have to go over real quick, and that is a special relationship between Km and S. Alright, so I'm just going to make this easy, and we're going to start out by saying I want a velocity that's half of the maximum velocity. So I'm going to set V to 1/2 Vmax, and I want to find out what substrate level is necessary to obtain this speed. So what value of S do I need to get half of the maximum speed? Well, when I put V for, or when I put 1/2 Vmax for V, I get this equation. Now let's simplify that a little bit. I'm gonna cancel out Vmax on both sides, divide Vmax on both sides, and I'll get 1/2 equals S over Km plus S. I'm gonna cross multiply. I'll get 2S equals Km plus S, subtract the concentration of S on both sides, and I'll get the concentration of S is equal to Km. And what this is telling us is when the concentration of S is equal to Km, I have the velocity equal to half of the maximum velocity. So whenever S is equal to Km, the reaction is going at half of its maximum velocity. And also you can go vice versa on that. If a reaction is going half the speed of its maximum velocity, then I know that the Km is equal to the S, or the S is equal to the Km. So there are the three equations that are important for Michaelis Menten equations and calculations and ideas. And I hope now you can understand how each term is derived and what is contained within each one of these terms.